the title in the sense that my group have been doing, I would call it machine learning for science for the last decade, if not longer. And I was at the DOE workshop last about a year or two ago, and they used the term scientific machine learning. So I thought I'll borrow that, it's shorter. And then the empirical rigor is something we have been struggling with to interpret the machine learning results. So I hope we get more people to discuss with us and have some understanding when we can take machine learning results and call that science. The machine learning, I had a little back and forth with Nathan yesterday, but he's gone now. So I definitely see machine learning as a part of both computer science and statistics, prediction, optimization, and cross-validation actually came from statistics in the 70s. And machine learning had very impressive success in IT. And I would like to argue that both prediction and cross-validation actually embed scientific principles, both prediction and replication. And with data ability, huge amounts of human label data, computer availability, and open source software. So we're seeing a big successes. And if I attempt to define scientific machine learning, it uses machine learning for scientific research to track from data, discoveries, theory, and knowledge. And it also builds scientific principle in machine learning algorithm, which we saw a lot of talks yesterday, try to get physics principles into deep learning. I like to think that we should iterate between the two steps. And then we have new principles. That's how we help progress of science. And empirical rigor, I just basically Googled and then get a definition from Wikipedia on empirical research process from observation, induction, deduction, testing, and evaluation. And then the word rigor, to define empirical rigor as empirical research process with the quality of being extremely thorough, exhaustive, or accurate. But what's extremely thorough or exhaustive or accurate, you often judge by a human group, like peers, reviews. And if I try to expand the empirical research cycle into the more data science or scientific machine learning, you start with a problem, you do data cleaning, visualization, and then the typical modeling stage. But at least for my group, data cleaning takes a huge amount of time, easily 80% of the time, that we don't talk enough. When you don't have good data, then all the models and algorithms don't really help you as much if you have bad quality data. And then you analyze the results, and you interpret that. Hopefully we have new scientific theory. That's what I'll try to go for in neuroscience example, and get new data, and then have a new problem. Interpretation is actually very key for, I think, for scientific machine learning, because a lot of the judgment calls will be made by fellow scientists, and if things are interpretable, make that judgment call a lot easier, and just for people to communicate. And EU already had a regulation in 2016 that even from the user point of view, we want machine learning algorithm to be, or statistical algorithm to be interpretable. So interpretation is definitely there. I have been pushing for stability for the last decades also. In the beginning, I was really trying to use stability as a very common sense principle to integrate a lot of ideas in the literature, both data perturbation and also model perturbation. And then recently, I've been pushing back to model formulation and data cleaning. You also have to think about stability issues. Often you have multiple ways to clean your data, and you want to make sure that your scientific results are not artifacts of the data cleaning. And also for model, for problem formulation, you have multidisciplinary people work together. Even words don't exactly mean the same thing. So you also need the problem formulation to be stable. Interpretability and stability, and recently we have got into causal inference. We also try to really help generate hypotheses for scientific experiments. So kind of really aid in scientific investigation. In a nutshell, stability is fundamental after predictability. Both, of course, need computability. Open stability really require even more computation because you have to do multiple routes. And you define a target of interest relative to the domain problem. Say you care about prediction, and predictability and stability become very much aligned. And you think about data perturbation, usually for ID data, bootstrap, subsampling. But I also want to bring in things which are not probabilistic, like PDE-driven models. That can be viewed as a form of data perturbation of synthetic data. And also adversarial data. If you say you're in a bank, and you care about the most risk the bank going to face through stress test, then you definitely don't want to add things to your model like kind of in the middle of your data. You want to put on outliers. So those of that is really problem dependent, but like to really unify both PDE type of models and probabilistic models under the banner of stability. And of course, the appropriateness of the perturbations is completely up to the people who use it. And I like to acknowledge subject knowledge, experience, judgment, and many, many other factors that we don't talk enough in the data science community. It's really, things are pretty subjective. We make a lot of choices and really try to bring a bit the liberal art thinking and debate into the data science discussions. As I said, the data perturbation, you have the simple ones. For the dependent case, how do you perturb the data? It's actually very much, I would call the frontier research on the stability. And adding small noise, I think was mentioned yesterday at some of the talks, that my late colleague Leo Brahman was definitely trying often just add small bit noise to both noise and the response variable and the axis to introduce stability. And people are more used to data perturbation, but I want to really put the data perturbation together with model perturbation. And the project I will share, we have easily 18 models. And how do we get some coherent theory, if we want scientific theory, out of that? And the earlier examples of model perturbation probably goes back to robust statistics by Tukey, who want to think not just Gaussian models, but also Laplacian and other type of models, so that the measure of a center of a data become robust. And sensitivity analysis has been done a lot in Bayesian modeling, also causal inference. So this concept has been around. I'm just trying to unify it under stability, but I think the stability up to data cleaning and model formulation kind of new. So put it together, I've been calling this PCS workflow for empirical rigor. That's not the only thing we should do, but I think this workflow will help us to do more empirical, rigorous research. Predictability in the PCS flow really works as a reality check, right? I have definitely too many talks, both in statistics and machine learning, people concentrate more how to fit instead of saying, does the model capture anything about the data or the reality? It's like fitting become a goal of itself. Of course we do fitting, but if it doesn't capture any reality, I don't think why we need to fit. And computability has been the center of machine learning, definitely. We also borrow that, and I'm adding stability on top of predictability and computability as a third base. As I said, it was motivated for reproducibility and interpretability, and also as an extension of uncertainty assessment. So you can see statistical uncertainty as a narrow form of stability when you have a well-justified probabilistic framework. You want to look at sample-to-sample variability. So that's a specific form of stability. But I'm trying to enlarge the tent to include data cleaning stability, to have perturbation come from PDE. So other things you can talk under the same banner instead of like, well, if you do probabilistic modeling, you cannot deal with PDE. But that's what people do in practice. We might just put it together and do a PCS inference. I won't have time to talk about our perturbation intervals instead of confidence intervals. When the probability framework is not justified, I don't think we have the right to talk about confidence. And often we have data, people start talk about probability model without really saying why there is a need for probabilistic description. So, but perturbation intervals, I think, is more transparent, more straightforward. You perturb data this way, and that's what you get. And if you can justify this is somehow mimicking a generative process, then you should write a page or two to justify that's the case, and you can call confidence intervals. Other than that, you're just doing perturbation. To go with it, as I alluded to in the last sentence, is that you really need to do documentation. Otherwise, it's very hard to judge. All this choice of metric, how you did data perturbation, makes sense. So you have to use a well-documented, like a reproducible, say, IPython book or R Markdown to describe your reasoning. That's very much like liberal art. You make a case with English or whatever language you want to use, and with the codes. So people can reproduce and judge. Oh, you do this form of bootstrap. Assuming IID doesn't make sense. Instead of saying, well, we hide behind symbols, we have X1 star, X2 star, and that really lose people and also make our work less rigorous. So for causal inference, that kind of goes by my like holy grail for causal inference is statistical laws, and my physics not statistics physics laws, say Hooke's law. Then there is mechanistic and very individual. But even for that, it doesn't hold all the time. If you got unlucky, the spring is going to break, you have too heavy a load, that is not going to work. So nothing really holds 100%, but it's a lot more replicable and stable than, say, I'll call statistical causal effect, like when FDA decide whether a drug should be released, they're looking at population level and see whether this new drug really improves on the average level. But the statistical causal inference is also moving towards closer, I think, to mechanism in the sense that we're now looking at precision medicine and we're looking at subgroups. We want to make sure the drugs work not just for the average, but also for a particular subgroup. Causality implies predictability and also stability. So the thinking here is that if you have predictability and stability, first I said stability is for interpretation, and we can also use this as a stronger, I would say, recommendation system than just predictability for intervention design. I've been talking about interpretation, and my group have been working on, we like interpret machine learning for the last almost like 10 years, and finally we got different people together. So my group we do genomics, do neuroscience, we do many different things. We thought we're in a unique position to really define at least what we think should be interpret machine learning, so that we have a more solid foundation to discuss among different people. So I won't have time to talk about, we have a paper out on the archive, and we basically have this PDR, etc. You need predictive accuracy. Basically, that's kind of your connection with reality. And then you also descriptive accuracy, and the good properties of descriptive accuracy include sparsity, simulability, modularity, and also domain-based feature engineering. And then everything are tied together by relevancy. So the predictive accuracy has to be relevant to the problem you want to solve, and the descriptive accuracy also is relevant to the problem solved. It's related to the human community and also to a particular problem. So for the rest of the talk, I will just share this work has been going for 4 years with Jack Galant's group. I've been led by 2 students, a former student, Reza and Yuansi and Adam, and with people from Jack's group. So we had done the predictive analysis at least 3 years ago, and for the last 3 years, we've been struggling, trying to do science and try to convince ourselves and peers that we have some scientific information coming out of this machine learning kind of exercise. So why I talk about neuroscience in an ML for physics workshop? And so I was Googling physics and neuroscience. One thing popped up was some APS news. 2016 said, physicists, the brain is calling you. And neural network was motivated by neuroscience, right? We have a lot of talk yesterday. Actually, 2 biophysicists, Hodgkin and Huxley, got Nobel Prize based on their work, try to model a single neuron through kind of electric unit with a bunch of, a series of ODEs. And then Hopfield was groundbreaking were neural networks. Hopfield was a physicist. So that's my kind of excuse to talk about neuroscience, since I don't know physics. And neuroscience and deep learning, definitely, if you talk to neuroscientists, many of them don't think deep learning capture much about real brain. But you talk to deep learning people, they think somehow it's called superhuman, right? Google used that term superhuman, so people feel like they already got it. So there's a gap. But there's similarities between human brain and artificial brain. So the data come from a particular visual area called V4. The 2 information streams going up in our brain about visual information. One is what pathway, one is where pathway. So I'm looking at the what pathway. We try to decide what we're looking at. So it's V1 is kind of Gabor, talk, and then a little more complex, and then V4. V4 has been a very elusive area for neuroscience. because it's not really IT, which you have object recognition. And it cares about complex shapes, but it has been hard to characterize what are the complex shapes. So one tradition of physiology from the award-winning Hubble and Wiesel work was try to find out what type of stimuli a particular neuron likes. So they tried bars and different orientation, different frequency, and was the basis for one of the Nobel Prize work they did. For V4, Pierre Galland, my collaborator, a long-term collaborator, have been working on V4 since his postdocs, right? So all the papers. People just made out this kind of pretty geometric shapes to probe. So they try. They think of something and they see whether neurons fire up. They kind of knows autonomy where the V4 is supposed to be, and they try and see what happens. So this is not very efficient, and it could be a lot of shapes we haven't made up that the neuron care about. We also try this different concave and convex boundaries, so very, very geometric and designed very. So Galland lab, this is from 10 years ago. Actually, Will Baumann, Wilmot, now at Oxford, collect this. It took him, was a postdoc at JXLab. It took 10 years. So it's very expensive data. Just work with the macaque behavior. And was black and white because database was not that available. And since I'm kind of a little slow with time, I'll say that my group engagement was from my postdoc Julian Morel and also Yuval Benjamini. Has never have been written. We did 2-layer dictionary learning and got the state-of-the-art result. Then the Carlos group at MIT have been pursuing various forms, and they really have called semi-natural images. We have natural images. They have objects imposed on a natural background and had very good predictive results. So our result really replicated the predictive result because they did the predictive result felt like we want to do interpretation and understanding. So that's been taking us 3 or 4 years. So the 2 scientific questions we tried to answer: what do V4 neurons do? And really how much convolution networks resemble brain function. What we did was using transfer learning and obtained very good predictive results and then try to predict. So what do we mean by transfer learning? So we took, say, AlexNet, completely trained on ImageNet, and used it as feature extraction. And we just put in our black and white images and made 3 channels the same and did feature extraction. So the ImageNet had nothing to do with our data. And then we did very simple linear regression and predicted our neuron activities. So in 3 senses, these are transfer learning. We had the feature extraction came from human data, very high level task, to kind of monkey data, and at a very micro level for single neuron prediction. So the thesis is that if the early visual cortex are kind of roughly captured by AlexNet, and then we try to replace the pre-processing by the AlexNet, and we connect with V4 data through some simple linear methods. As I said, the Morel et al. Work was state-of-the-art, and we tried this. That work took us 2-3 years. I had 2 of my best people, a computer vision guy, Julian Morel, my applied statistician, Yuval Benjamini, and took a lot of time to get there with 2-layer deep learning, and this just beats it slightly. So that's why I started working on deep learning. I felt there's something there. If you look at the performance, actually not just the 2nd layer, other layers work pretty well too in terms of 71 neurons. But Gabor definitely does a job. However, you not just have AlexNet, right? You have VGG, you have GoogleNet. We didn't continue with ResNet, all the other things. And they give very, very similar performance. The 3 lines, AlexNet, GoogleNet, VGG, basically on top of each other. And the dotted line are the data. So they all kind of dump down a bit, possibly because the training data is only 1 replicate, and the test data is like 10 replicates, a higher signal-to-noise ratio, and you cannot really reach the details of the structure by very noisy data. So quickly, we take second layer, third layer, and fourth layer, and two methods, ridge and through regression, we end up with 18 models and correlation between this prediction proportion like 0.92. So they technically really do as well with each other. So the question is, how do we interpret and get some science out of this? So we went for stability and say we want something not just data perturbation, but also stable across this 18 models. We borrow idea from Deep Dream and say that we have these 18 models. What if we just maximize the fitted models? It's kind of similar in idea from what people like the Nobel Prize winner did for V1. They were looking for signals that excite the neuron. So we're saying if the models are good, we want to see what are the signals excite the model neurons. And that was white noise. We actually did a little regularization, so that's why we didn't try to call deep dream for the particular regularization. We call deep tune. And you end up with this curvature-like maximizing signals. We have 18 models, and we did all of them. That's the 18 model results for this particular neuron. They're different, but they all have this kind of curvature, like coarse level pattern. And for a while, we're just happy that it seems like they all like curvature, so this is neuron with curvature, like curvature. And then we did decompression. We removed like 40, 60%, and you still see the curvature remain. Right? So it's another form of perturbation. We're just removing nodes, depends on the prediction performance. And when we look at the small database we have, and what are the signals excite the model neuron, and you also see curvature. And then we went back to the original data without any modeling and look at the high peak of the signals, you still see curvature. But people really wanted us to give one signal, so we brought in stability principle at the gradient level, and we got the consensus smooth deep tune. So basically, at each one you do this gradient ascent, you take the slowest slope, and you keep moving. So for neuron 1, this is 10 different initialization for consensus, so you get very, very similar results after you aggregate the different 18 models. Then you can cluster using hierarchical clustering and correlation. You see these complex patterns, contours, which we know people find out already. So, and also these textures, which people already, we didn't show, people kind of also know before. So we kind of really replicate a lot of results, but through deep learning, and also have more naturalistic looking stimuli than what the geometric shapes. But then comes the question, actually the referee really pushed us. We sent a PNS direct submission that which part of you see is really from the neuron, which part is an artifact of your model. And one question the referee brought up was, does the neuron really care about small patches of curvature or big patches? And actually, while I gave a talk, Shirley asked me to give a talk at the IBL a while back. And then the physicist there was saying that there's regularity. You see between the curves, there seems to be a period there. And it is actually an artifact of size of convolution network, a convolution filter. And that creates this periodicity. This just shows that the neuron care about small patches, and then the big patches just kind of add up, compound the responses because the convolution filter move around and add them up, and you have a more enhanced result. And same thing for another pattern. And we also try to take piece out and see whether the neuron care about. So there's some, for the first neuron, you can see that you have this one curve, you have 14, the top was 34, the maximum of the model response. And you also have, you mask the image. So this is where the receptive field is. So outline shouldn't matter, you have pretty high. All of this try to convince ourselves that we actually have some signal that's real, it's not because model. The reason I say that the regularity between these curves is due to the convolution filter. You look at Google Net, it has a smaller convolution regularity decreases. So that's the evidence show that this regularity is not because the neuron likes this, it's because the artifact got modeled. So this is a general question we have to face is how much we read out the results because the model structure, how much is really about the data. And in the end, this is not a proof. This is only suggested. So working towards, I'll call scientific recommendation system, these patches of images can be a starting point to do closed loop experiments. So if the electrode's still inside the macaque's brain, then you can feed back these deep tune images, or you can take small patches and do random combination of that to see what to prove that this neuron really care about curvature and at what scale, which we couldn't really resolve. And this is just look a lot more naturalistic than what people came out with. And hopefully they would increase the efficiency of experiments. To end, I want to point out that PCS documentation is very necessary. Models are mental constructs in our brain, and there's reality. You really have to use quantitative and qualitative narratives to bridge the reality from to the mental construct we dreamed up. And this is an example for genomics. So we also had some genomics work along these lines, and there we had some validation in the literature about the gene-gene interaction we find. So that's there we also serve as a recommendation system. So to finish, I try to advocate stability as a basic scientific principle after predictability, because reality check. I showed one study to drive generation of hypotheses, and also the documentation is very important. The structure match are very important, even we have lots of data. I think that was already reflected in yesterday's talk. So here are the papers, and we're working on a book with my student, Rebecca, to use these principles, try to lower the entry level for data science and statistics, and open questions. So I like to believe, that's what I'm doing, is the PCS framework is a step forward towards scientific machine learning with empirical rigor. But do we need to set up some consensus on what we agree? Like what type of work you start with machine learning? And you will say that this is really like a scientific knowledge now. Do we have things we can write down for especially students and beginners or among ourselves? When we do referees. I mean, I'm on the editorial about PNS, and a lot of papers I'm getting is really at the interface of science and machine learning. And I personally have a very hard time, especially a subject area that I'm not familiar with, to really judge to send it out. Because they run some machine learning algorithm and have some results. And is that science or is that just prediction game? So I find it very hard, and it's very hard to find referees and guest editors, all of that. But there's a lot of people in this space now, and most of my papers actually are in this science and machine learning. And myself often find it a loss. So I hope to get you guys to help me, like, when does machine learning result cross the line become science? And what are the things we should look for? And how can we really be accepted as like at least playmates with scientists, right? I mean, John Tukey used to say that statisticians get to play in everybody's backyard, and now we try to play a bit in their front yard. Like, do we have the credits to do that? Depends on what we do. And from these results we have obtained, right, definitely debate among authors is the first step. And then peer reviews. I think our referee for our deep tune paper really push us to the next level. We were just happy to take deep tune as somehow characterizing the neurons, but with all the questions that one of the referee asked, we realized that we cannot really make that claim. It's at best suggestive, so we have to retreat from our claim. And also, of course, I'm looking for physiologists to work with to see whether this closed loop experiment can be done, and they like it, to say that, yeah, that's helped me to design experiments than without machine learning type of algorithms. Thank you. after feature after feature extraction.
What I mean is that it, when you show that, aren't you putting yourself into a framework of a linear model for the neurons
Well,
response?
I mean, we do go through the environments introduced by the feature extraction from the AlexNet, right? So so after that, you definitely do a linear model, right? But I thought the feature extraction step make it nonlinear overall, right?
So, for example, if any of these neurons is invariant to rotation response, what kind of, which we find a lot in neural nets, there are a lot of neurons whose response are invariant to rotation.
The V4 neurons, we haven't seen in previous work saying that they invariant to rotations. That's a bit of evidence saying that probably is not what we're seeing here.
Okay.
So that's our work doesn't really refute that, but I think from
Okay, so you would think there is no such invariance coming in that
at
would
least
explain
that's
what.
not what we believe.
Okay.
Right? But it will be interesting. That's the thing when we put back. If we get some lab to work with us, right, we can do this and we can do a lot. Jack doesn't do physiology anymore, even
Okay.
he got this data. Yeah. So it's a that's so it's like there are a lot of other hypotheses. That's why we couldn't say we really do science. We're kind of helping science by coming out with some. Right. You don't dare to claim that we can replace science, but we hope we can make science more efficient, take advantage of big data. So, so that's kind of the framing my group is doing also with genomics. I asked a biologist, how do you decide what experiment to do? She said, I read papers, I think about it, and then I decide what experiment to do. So we're hoping that maybe you should also look at our model results. Maybe they'll help you, just like doctors, to make your decision. Yeah. Thanks.
This on like the interpretability in terms of humans being able to kind of the narrative side of what's going on. When and then you're doing these perturbations and you're showing lots of results and how they change. In those cases, they're all images, and so we as humans can look at them and kind of maybe it's not quantitative, but we can kind of quickly assess something. One of the difficulties for me is trying to figure out how you do that when it's not when the data does not look like images, basically. And where it can be much harder to try it for a human to kind of quickly assess what's going on with the data or what's being presented. And I'm just wondering if you have kind of general thoughts about that.
So I think you do have to have stability. You're really talking about metric to assess stability, right? So I use visualization to convince you, but also we had a deep tune to make it more quantitative. For genomic project, we have iterative random forest. There, we use decision trees, so it's kind of interpretable too. And then we end up with a stabilized version of gene-gene interactions. So you have to somehow bring in something which you can look through, right? So interpreting the features in deep learning, we know has been very difficult. But when you do the neuron part, because people care about what stimuli a neuron gets excited, so we're kind of building on that. By talking to Jim DiCarlo from MIT, actually he wants physiology to move away from this qualitative. He wants to be more automated. So the two groups have a kind of back and forth debate. He basically said, I want to do away with any human involvement. I want everything to be AI-like and automated. And we push back, said you probably need both. But it's the stability metric that, I mean, we all love L2, but it's not like we have a lot of evidence L2 is the right thing either, right? Not getting a community to agree on something and these make progress, and you have downstream, I would say, advantages you can see. People might try different metrics before we know for a particular domain problem what might make sense, but you need a downstream kind of results or validation to see.
You are probably the one who has thought about it most, so we wanted to pick your brain on what you think when will the machine learning become science question. What do you think the answer is? When it will become knowledge? What are the things the community needs to impose in order to make it knowledge?
I feel like for one thing, we need probably just like a scientific knowledge. It's best to be replicated by another lab. So in the beginning, we thought Jim DiCarlo group did our work, but later we saw it was actually positive. We were kind of independent, did the same thing, and get similar results. So that was a good thing instead of, oh, Jim did first. So it's a replication. We didn't know they were working on it because we have been going after interpretation, so it took us a lot longer, and we saw their work. For a while, we felt bad, and later we felt good because we actually replicated what they did, which related, not exactly the same problem, but very related.
Application, I think if another lab uses your result,
yes,
that's when it's knowledge,
yes.
right?
No, but I think replication is a lot of time the first step before somebody else wants to.
Absolutely.
Yeah. So for the genomics project, is that our scientific collaborator Sue Seneca's lab is ready to take our recommendation and do experiments. So that's also a step closer to doing science. They're willing to spend a few months to try out. And so in some sense, use our result. But I do think that we could do a lot more stability type analysis. It takes computing power to make things more trustworthy than just one pipeline, one particular processing method, one particular model. And for me, I felt like we need to move away from that just because we are trained in Bayesian model, we do Bayesian model, I'm trained in Lasso, I'm doing Lasso, and just seems very arbitrary. Depends on your training, that's how you attack the problem. And that's just very not objective. Thank you.